the fundamental theorem of calculus actually has two parts. It's got a fundamental theorem of calculus part 1, and then there's a fundamental theorem of calculus part 2. Okay? All right. So like what I've said a couple of times before, usually theorems in calculus are pretty much, common sense ideas, right? So let's just read them. Let's see if we can make sense out of it. If f is continuous on closed interval AB, right? So visualize a continuous function. Then the function f of x, this capital F, is equal to the integral f of t dt, right? So that function, so f of x, right? So what is f of x? F of x, we're going to define it as the integral of little f from a to x, right? The area underneath it. So then, if f is continuous, then this function f has a derivative that looks like this. So if f is the integral of this, then what would the derivative df dx look like? Well, if I wanted to take a derivative of this, ddx of this, that means I would have to take ddx of this integral, right? Okay, so conceptually speaking, if you take an integral and then take a derivative, what do? What are you doing? How are those two related? You undo what you've done, right? So if you take an integral and then you take a derivative of that, one cancels the other in a way, so you end up with your f of t, the one that was inside. Except what happens in the process is, look here. Whereas originally, f was a function of t, after this process, f will be a function of x. So what happened? Where did that x come from? It was the limit of integration. So do you see how this is f of t, but we're integrating from a to x? In the end, you get the function, but the variable has switched from t to x. Okay? Now, when does this work? This works when you're integrating from a to x, a constant to x. Not from x to a, not from a to b, not from x to 2x, but from a constant to a variable. Okay? That's important. Okay? All right. Let's explore this a little bit. So suppose I have an integral from 3 to x, t cubed dt. Okay? And now I want to take a derivative of that one. Okay? Let's see how that works. Okay, so you know what? That ddx, let me just leave it there for a minute. Let's see what's going to happen here. All right. I want to do just the purple part. I'm going to ignore the red, just do the purple part. So that's going to be t to the 4 over 4. Is that right? And it's going to go from 3 to x, right? Yes? Okay. Now, this is going to equal to, okay, I'm still going to ignore that ddx because I don't know what that is. That's just too confusing for me right now. Still the purple part, what we learned yesterday in the class before that. What happens now? You put the upper limit of integration in, so x to the 4 over 4, minus, then you put this one in, 3 to the 4 over 4. Okay? Okay, now I can't really go any further with that. 3 to the 4 over 4, it's some number, I don't care what it is right now. Okay, what do I have now? I have ddx of this minus that. Okay, so I know how to take a derivative, right? Can I take a derivative of this purple now? Mm-hmm. Okay. What'll happen if I take a derivative of x to the 4 over 4? 4x cubed over 4 minus, what happens if I take a derivative of that? 0. So what do I get in the end? 4, no, just x cubed. Just x cubed. Okay, what did I do and what happened? I integrated a function, then I took a derivative. Okay? I had t cubed. Look, I have the same function, x cubed, right? Everything else that I did went away. But what happened in the process? The variable changed from t to x. Okay? So you integrate, blah, 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 and then when you take a derivative, you get the same thing back with the new variable, and then all those constants will go away because the derivatives are zero. That's the fundamental theorem of calculus, part one. That's it. Okay? All right. So now let's do a couple of examples.
So couldn't you just replace all of the variables?
Yeah, you can. That's what we're going to do.
Yay! That's
You just, no work. What? Okay. Except if it's a different function. Okay. So when are we going to apply this? When does the fundamental theorem of calculus, FTC for short, apply? When you have to take a derivative of an integral. Okay? You have y equals, and you're looking for dy dx. All right? So here we go. Find dy dx of an integral. Derivative of integral. Okay. Let's see if this qualifies. I have a number and then a variable here. Yeah, it qualifies. So what I do is I take the x and I just substitute it for any of the other variables, or for the t rather. So this will just be 1 over 1 plus x squared. And with that, I'm done. That's it. Wow, I know. Okay, it's beautiful. Here, let's see if this will work. Right? So let's see if this will work. So okay, so another way of writing this. What is it that we're doing? This is y. What do I need? I need dy dx, right? Well, another way of writing that is d dx negative pi to x cosine of t dt. On a test or a quiz, you might just be given this. Don't get confused what you have to do. What do we have to do? What'll it be? What'll the answer be here?
Cosine x.
Cosine x, that's it. Why can we do that? Because it goes from a number to x. Okay? Okay, now they're not all going to go from a number to x. They're going to go from a number to some function of x. In this case, use the chain rule. I know. Okay? So, when the variable is different from x, do the same thing, but multiply by derivative of upper bound. We can do this. Okay? All right. So take a look here. We're going from 1 to a different function in x. So what do we need here? We need d dx cosine of t dt, and we're going from 1 to x squared. So, first off, it's cosine, and the x squared goes inside the t. Now, did I plug in x or something other than x? Other than x. So, I multiply by the derivative of this, 2x. Okay, chain rule. Yeah, so this is just 2x cosine x squared. It's we always write algebraic functions first. Okay? All right, here. d dx of this mess is equal to, okay, now the negative 2x is going to get substituted for u. So it's going to be negative 2x cubed, right? Minus 5 times what? Times negative 2. Okay? So be careful that you don't get lost in those, little algebra steps. So this is now negative 8x cubed minus 5 times negative 2. You cube everything. So x gets cubed, negative 2 cubed is negative 8. So 16x cubed plus 10. Whoopsies. Okay, we're good?
Why you multiply by -2?
Because it's the chain rule. When this is a number other than x, right? When it's not x, it's something else with x, you have to multiply by the derivative of that number. Okay, and the derivative of negative 2x is negative 2. Okay? All right. Okay, now look at what's different here. What's different here for A? Okay, this time the x is on the bottom, right? But our fundamental theorem of calculus was defined with the x on top, the variable on the bottom. There you go. You switch it and make, look at you guys. Who's teaching you calculus? Okay, so switch it. And then 5 to x, 3t sine t dt. Okay, so now we need ddx of that whole thing. All right, the variable is just x, right? So it's going to be ddx of negative 5 to x, 3t sine t dt. So that's going to be negative 3x sine x. Okay? That's the answer. Okay. Now look at the next one. The next one's a little bit more complicated. Why? Because there are two variables as the limit of integration. Okay, you can't have that, right? Well, we're going to split it. Yeah, so the issue here is you can only have one variable as a limit. Okay, so what we're going to do is we're going to split into two regions. Okay, now between 2x and x squared, which is the smaller? 2x. Can x squared be negative? No, x squared as a whole is always positive, greater than 0, right? Can 2x be negative? Yeah, okay. So, if this is 0, x squared is always higher, right, than 0. 2x can be lower because x can be any number. So now look at what I did. 2x to x squared, I can split it into two regions. One going from 2x to 0 and another one from 0 to x squared. So you have to do it twice. So what's going to happen is I'm going to rewrite this as integral from 2x to 0 of e to the t dt plus 0 to x squared of e to the t dt. Now is this okay? No. You have to flip the first one because the number, the 0, has to be on the bottom. So this is now negative 0 to 2x e to the t dt plus 0 to x squared e to the t dt. And you thought it was just a one-stepper all the time.
I'm glad it isn't.
I know, right? So now what I have to do is I have to take ddx of this entire thing. Okay? So what happens for the first one? 2x goes where? Into t, so we have e to the 2t, then times 2, and of course there is a negative out front. 2x, sorry. Okay, plus, what about this one? E to the x squared times 2x. Okay, so this is now negative 2e to the 2x plus 2x e to the x squared. Oh my, I know. That was beautiful. We leave it like that. You really, I mean, you could factor out a 2, but not worth it. It's good, right? Good stuff. Okay, that takes us to, yeah, the fundamental theorem of calculus, part 2. So part 2 says, if f is continuous on every point on AB, right? Okay, so what happened here? Look at what happened here. We went from 0 to a number, or we went from, A to 0, 0 to B, right? In the end, what we got is this plugged in, so A plugged in here, f of A, and then f of B with a minus sign in the middle. Okay? So, if, that's the second part of the fundamental theorem of calculus. If we're integrating from A to B, f of x dx, then that's just f of b minus f of a. Okay? This is called the integral evaluation theorem. Okay? All right. So basically, what was f? Do you remember here what f was? F is the antiderivative, right? So that's the big deal. It's the antiderivative. All right. So here, when we integrate this, let's do a couple of these. Similar to what we were doing yesterday. When we integrate this, what do I get from the 4? 4x, integrate. 4x plus what? 2x squared over 2. Right, and that goes from 4 to 6, right? So this is 4x plus x squared, 4 to 6. So what happens now is I plug in the 6, and I get 4 times 6 plus 6 squared, minus I plug in the 4, 4 times 4 plus 4 squared. Yeah, then you just, it's going to be 24. What is that? So basically that's 28.
The first part comes from when you do like in the last chapter when you like n plus 1.
Yeah, last section, yes. All right. Remember, when it's from A to B, the lower number has to be the smaller number. Like the number on the bottom has to be the smaller number in value, right? So negative 1 to E, smaller value, larger value. All right, so what about this one? What's the antiderivative here? E to the x, and it goes from negative 1 to E, right? So what is that? E to the E minus E to the negative 1. E to the E, that's fine. That's like 5 to the 5. We can live with that, right? But what about that one? Minus 1 over E. And that's a good enough answer. Don't go plugging in stuff to your calculator. You can leave it that way. That's perfectly acceptable. Okay? Because remember, sometimes you plug it into your calculator and you transfer it wrong from your calculator to your test because you're rushing. So just leave it that way. Okay. How about this one here? So with these ones, you really have to be careful that you keep track of your negatives and your exponents and all that stuff, right? So here, I get x to the 4 over 4 plus x negative 1 to 3. Okay? So when I plug the 3 in, I get 3 to the 4 over 4 plus 3 minus negative 1 to the 4 over 4 minus 1. Right? So that's 3 to the 4 over 4. Wait a minute, that's 81 over 4. Plus 3 minus 1/4 plus 1. And look here, this and this, that's 80 over 4, which is 20, right? Plus 4, 24. So definitely can be on a non-calculator section. I know. That's why you have me, to give you these tips and tricks. Okay? Except if you're taking a test. Okay, so this one, I'll do this one with you and then I'm going to have you guys do the next two. So x to the what here? 5 over 2 divided by 5 over 2. And in this step is where I need you to be quick. Here now, that's going to be 2 over 5 times x to the 5 over 2, right? You divide by a fraction, you multiply by its reciprocal. Divide by 5 over 2, multiply by 2 over 5. From 0 to 4. So, 2 over 5, 4 to the 5 over 2, minus 2 over 5, 0 to the 5 over 2. Okay, so that's just 0. But what about here? 2 over 5. Okay, so what's this then? What's, Right, but like, what's 4 to the power of 5 over 2?
4 times 5 over 2.
So square root of 4 to the power.
So basically, 4 to the 5 over 2 is equal to the square root of 4 to the power of 5, right? And root 4 is 2 to the power of 5 is 32. And that's 64 over 5. All right. I'm going to give you 2 to 3 minutes to do E and F. I'm going to pause this for a second. First step is negative sign. The antiderivative is cosine. And we're going to go from pi over 6 to 5 pi over 6. So cosine 5 pi over 6 minus cosine of 1 pi over 6. Okay, the pi over 6 is here, right? Looks like this. That's the small angle. Cosine is this side, so that's root 3 over 2. Okay, now 5 pi over 6 is in the second quadrant, so it's negative root 3 over 2 minus positive root 3 over 2. That's negative 2 root 3 over 2, which is just negative root 3. Okay? Fantastic. Okay, this one, what do you do first? You distribute first, because otherwise, you would have to do it in a method that we haven't learned yet. But, okay, so we're going to distribute negative 1 to 0, x squared plus 2x plus 1 dx. Now integrating is super easy and fun. X cubed over 3 plus 2x squared over 2 plus x from negative 1 to 0. All right. So this is just x squared here, right? Okay, so if I plug in the 0, here I get 0 plus 0 plus 0, so that's 0. Minus, now I'm going to plug in the negative 1. So I get negative 1 cubed over 3 plus negative 1 squared minus 1. All right, so what is that? Negative 1 over 3 minus 1 plus 1. 1's go away, 1/3. Who would have thought? E and F, such cute little answers after all that. Okay? Okay, now, total area. You've got a function like this, and look at this function. Most functions are not just going to be above or below the x-axis. They're going to fluctuate, right? So, how to find the area between these, between the graph, the function, and the x-axis? So basically what you do is you partition the interval with zeros of f. So look at this one. We want to find the area between y and the x-axis from -2 to 2. And if you graph it from -2 to 2, look at what it looks like. That's what it looks like, right? So here the area is above, below, and above. So what you do is you cut off the interval by the zeros of this parabola, of this function, okay? Where are the zeros of this? Let's see. 3x squared minus 3 equals 0. X squared equals 1. X is plus or minus 1. So this is at -1 and that's at +1. So you partition this. Then you integrate f over